All right, so let's take a look at this section. So remember, this is like a hodgepodge of like stuff, like a whole bunch of things that we haven't done related to a derivative yet. So remember, nope, h plus 1 minus 2x plus 1 and all divided by h. So remember, this is supposed to be equal to the derivative, f prime of x, right? And we solved this a long way. But what I want you to do is be given the limit. I want you to first find the f of x. Then I want you to find f prime of x. And then, and then what I wanted you to do was find f prime of some value a, which in this case, the value is pi that I want you to evaluate this as. To pick out the original function, see, the original function had the x plus h replacing the x. So this is like replacing my x. So that means that my original function is cosine of x. The derivative is negative sine of x. And I want negative sine of pi, which is 0. Okay. There's also a thing that you could do with limits. It's another technique for limits. I told you guys before, like, we did, multiply by the conjugate, simplifying the complex fraction, trying to factor it. There's another thing called L'Hopital's rule. Spelled like La Hospital. Lots of funny things come up when you type in L'Hopital's rule and I guess memes if you want. Notice something though, when we do this, it is the derivative of the top divided by the derivative of the bottom. This is not quotient rule. Okay, so limit. And this only works out when I have like 0 over infinity, infinity over 0, infinity over infinity, or 0 over 0. Okay. All right, so now I take the derivative of the top, which is a positive sine of x, divided by 2x. I still can't plug in 0, so I do it one more time. And I get cosine of x over 2, which gives me 1/2, because the cosine of 0 is 1. Okay? So that's L'Hopital's rule. Then there's like derivatives and where derivatives do not exist. So derivatives do not exist at corners, cusps, and discontinuities. Okay, what does that actually mean? At the end of the day, the easiest thing to remember, and I can compute these derivatives by the limit definition, but in the end, ultimately what you need to be able to identify is anytime I have an absolute value at the vertex, it is not differentiable. Means I can't take the derivative there. Really what it means is that the left side and the right side derivative does not exist at that point. It makes sense with absolute value because what do we have to do to drop the absolute value? Always ensure that the number plugging in is going to always be positive. That will not occur at certain values of x. So if I were to look at this would be the limit x approaches 0. This would be the absolute value of x minus 2. And then I would have minus, okay, hold on. I'm approaching the vertex, so it's not x approaches 2, it's x approaches, sorry, not 0, but 2. When I plug in 2, I would get 0 all over x minus 2. So if I'm going from 2 from the negative side, what ends up happening is when I drop my absolute value, right, I'm going to have to make this whole thing negative. And I get an overall negative 1. Now when I do this and approach it from the right-hand side, I have the absolute value of x minus 2 minus 0 over x minus 2. This is the limit as x approaches 2 from the positive side, a positive x minus 2 over an x minus 2, and I get 1. Those are not equal, so the limits are not equal. F is not differentiable. Oops. At 2, and this is called a corner. All absolute value graphs are called a corner. And then the graph, the equation isn't here. This should be x to the 1/3 power. Yeah. So limit x approaches 0 of x to the 1/3 minus 0 over x minus 0. So I get the limit x approaches 0, 1 over x to the 2/3 power. So realistically, I'm taking the limit x approaches 0. I'm taking the cube root of x, and then I am squaring it. That's realistically what is happening. So when I do this, and I can go from the negative side here, because we have to alternate. So I go from the negative side, it doesn't make any difference. I'm going to get positive infinity. Likewise, when I keep doing this, right, and I get to limit x approaches 0 from the positive side, I'm actually going to get positive infinity. But since the limit is infinite, and infinity is not a number, you can conclude that f is it will be a vertical. All right, so we can conclude that there is a vertical tangent. This guy's a vertical tangent. Okay, so now all right, so let's see. So now I just wanted to double check, make sure I did not mess up my definitions for you guys with vertical tangents and not differentiable. I just want to make sure I wasn't messing them up. Okay, so then this is okay, so now limit as x approaches 0 from the negative side, x to 2/3, oh my goodness, 2/3 minus, not 1, holy cow, x minus 0. Okay. Now what you're going to notice is that we're going to get, yeah. So now I'm just taking the cube root. So from the negative side, I'm going to negative infinity. When I do from the positive side, I get a positive infinity. And since both of them are infinite and infinity is not a number, f is not differentiable at, and then this is called a cusp. Okay. All right, so that is it for this lesson.